Welcome to today's lecture on causality for AI and ML. And today we will be covering the topic of causal representation learning. So before we have looked at mainly scenarios where we have a causal graph available, where a causal graph was like given to us or like we try to recover it in any way. We knew what the causal variables were, and we were kind of sure about the connections between them, and like modeled basically every scenario as a causal graph. So, but what you will usually experience in companies or real world settings is that you don't get like graphical structures. Like what you often observe are images, like a collection of pixels where it's not immediately obvious which kind of variables are present in the image. Furthermore, it's also not like directly visible which kind of relations might be present there. So for this row of dominoes, I think every one of us has a like intuition what will happen if the hand wasn't there, or how this scenario came to be in the first place by tipping over one of the dominoes. But how can we teach that to machines? Another example here. What is the causality in this image, right? So we see some sort of gridlock. We might consider the traffic lights. We might consider cars stopping for pedestrians. And most importantly, what we see is that we see no dynamics, right? So we see a like static image where in some very unlikely scenario, maybe all the drivers have stopped for some different reason, right? So maybe the cars are all moving backwards or whatever, but usually we don't assume that. We assume some underlying dynamics, some common dynamics from which we do not divert, except if we have like very good reasons to do so. But if we show that image to a model which has never seen such a scenario before, it probably can't make sense of it. It doesn't know what cars are, like maybe it doesn't know the driving rules, it doesn't know about traffic lights. So we might need to find a way or find conditions under which we transform pixels to variables, and then maybe also consider a temporal aspect. So how this image will evolve. And of course, this might be like general learning of dynamics, like a sort of world model. But of course, in this lecture, we will look particularly at like the causal aspects of this. So if we see such images, how can we make sure that our models do not learn confounded factors, that they learn the true underlying dynamics? And similarly here, where you see maybe the different seasons. I showed you this example before in the previous lecture. So here it's also the case that we do not see all the factors that are necessary. So maybe, and we will discuss this in a later lecture, it's also important to not only look at the data distribution for small examples, but with the rise of foundational models, LLMs, vision language models, to also expose them to data that goes beyond our specific use case. Because here we could correlate temperature and the background, but like the real driver of all of these changes isn't in these images. Yeah. So as I said, usually we as humans, I believe at least, we leverage temporal cues. We interact with the world to disentangle concepts. And basically, we predict the underlying dynamics to make inferences about the outcomes. Right. So what we saw 2 lectures ago was the concept of causal abstractions, where we considered how we can transform low-level models to high-level models, but like usually we considered both of these representations to be graphs. And there it was more about the consistency of these transforms. And now with causal representation learning, we are almost always in the setting where the low-level models entail no semantically meaningful variables, so mostly pixels or maybe some sound or like audio sequence. And the high-level variables are typically unknown. So we first need to recover them to find groups or clusters or some sort of representation that makes sense to the model and most importantly to us. Yeah, and with that comes that we usually don't know the causal structure as well. Yeah, and that's then basically the task to discover the variables and the structure from data. So I made a small table. Basically, if we consider the past lectures, so causal effect identifications assumes that variables and edges are known, or at least partially known. Causal discovery then knows the variables, but doesn't know the edges because that's the task to discover them. And finally, now we are in a scenario where both is missing. So actually, there is a fourth combination where we, for some reason, do not know the variables, but we know the edges. I'm not quite sure which setting that would be, but maybe it's structure matching. So we are going, we are maybe in a multimodal setting where we have discovered the structure in one modality and want to rediscover it. For example, we read about something in the text, and we want to rediscover it in images or something. But I think this, like, there isn't much work on that, and we will leave this. So the thing is, again, as we discussed before, what are variables? And here it's what are factors of variation? Because an important insight, if you like look at causal inference and so on in general, if you observe a constant, it can never be a cause. So things that don't change, at least don't change in our data set or in our observations, we cannot reason about because we don't have enough like variability in the data to infer what would happen if a change would be made. And equally, constants cannot, like we cannot infer them to be causal effects because again, if everything changes but our one variable stays constant, we might infer usually that it's not connected or not the effect of any of those other variables. So moreover, what we need is like some sort of variability and in that sense also enough information. So also if two variables always vary together, like we don't know, are they maybe the underlying same concept or are they different ones? So in this kind of sense, we need enough information from our data to disentangle concepts. Yeah. And the other idea, of course, is that we can have prior knowledge. So this is again with like foundation models with LLMs and so on. So they have seen a lot of data. Now they see our still image of the dominoes or of the cars at the intersection, and they already know the concepts. But usually with the smaller kind of models that we want to train from the ground up, we don't have access to that much data. And again, like I said, a single image usually isn't enough for training. We usually need either a population, which is then similar to causal discovery where you need some sort of like independent samples, or we need a series, for example, a video or something where we have a time series, and then we will leverage also that temporal aspect to infer causal structure. So yeah, maybe this would help further, even though it might not be enough to train deep models. But at least we have some variation, we have some interventions maybe, and this gives us already a lot more information about the dynamics and which of those dominoes might change or which pixels might change or not. Yeah. So maybe as a first idea, we will have a look at entanglement. And basically, the idea is if you are training computer vision models like VAEs or autoencoders, you have a network that takes an image, encodes it into a latent vector, and then you have another network that encodes the latent vector back to an image. And the optimization goal is to like have this image at the start and the end to be the same. And this latent vector is sometimes interpreted as a latent vector which contains maybe like sort of interpretable concepts. So it might contain in one of its variables the color of an object or like the type of an object and so on. But then for an image, there are a lot of other variables that also, or aspects that need to be encoded. It's not just, okay, this image shows a dog or a cat or something, but usually you also have like the lighting and background, the camera position that changes. And even though a set of images might always show dog, you have a lot of different styles in that sense, like how this dog is recorded. And so the first thing we want to look at is there a way in these models that we can maybe guarantee that our network disentangles content from style, which means can we make sure that it like focuses on the dog class or the class that is shown in the images and like is like does not consider the style when making decisions, for example. And yeah, what I told you before, for this there was a like special data set constructed. The problem usually with like observed or like real images is that we often don't have access to all the factors. So here they have a bunch of objects like a teapot, a rabbit, a dragon, I think it's a cow, and so on. You see different lighting conditions, different camera angles, and different poses or like transformations of the object itself in the scene. And what we would like to have is our object, our model maybe focus on all of those. So yeah, here you have it, position of the spotlight, position of the object, rotation, the overall class and stuff from the background. But then what the authors did was to also add augmentations, right? And you can think of it like these previous variables, those might be our content that we want to recover. But then we might have like cropping of the original images, random flipping, color distortions, random rotations by 90 degrees or something. And we might want to be invariant to that. So what can we do? What the authors propose is to use a kind of paired setting where we have the original image and some augmented image, as I said, like cropping or whatever. You can also do it with like two cropped images. The thing is that between those two images, the content needs to be the same. So you want to like record the same object maybe twice, but under a different camera angle and so on. so that the style variables change and the content is the same. So then what you can do is we can apply a sort of contrastive learning, which usually is a sort of, maybe let me continue, yeah. Which usually is a sort of loss function that tries to pull together images of the same class or the same type and pull apart images that differ. And what this basically means in our example, so if you haven't seen this sort of thing before, we use a similarity measure, which is basically on our, so we train a VAE, we look at our latent vectors set, and what we want to do is we want to have latent vectors of the same class. So we look at a bunch of images, maybe, I don't know, 20 or 100 or whatever. And for all of those images, we compute a pairwise distance of these latent vectors. And so if we look at every of those pairs, we might have a pair where both images show, for example, a cat. So we expect the similarity of this latent vector to be small. On the other side, since we have a lot of different classes in our data set, we expect the overall similarity between our first image, which has latent vector set I, and some random image to be greater, right? So there might be images which might also show a cat again in the overall set, but like on average, the other classes are going also into this lower term. So basically the idea is we want to promote or we want to have a loss function that promotes similarity in this upper term. So let the distance go to 0. Yeah.
Don't care to estimate these variations for one-sided.
Yeah, exactly. So maybe to like specify that a bit further. So what we want to have is to have our model to be invariant to these augmentations, right? So we want to learn the content, but not the style. You are correct. So in an autoencoder setting, of course, we would like to have that the image is truthfully recovered, which also means in this latent vector, there needs to be some information about whether the image is cropped or flipped or whatever. But what we want to have is that we want to, in this latent vector, then have two groups, where one of those groups is the content vector, and the other group is the style vector. And we want to have a clear separation between them. So yeah, thanks for the question. So basically, we do not want to have like that the image that the VAE doesn't know about the style. It doesn't need to know it because it needs to reconstruct the image. But the thing is that we want to have like in this latent vector a separation between these two groups, that we don't have like a or a value in set that should belong to or represent something of the content that is then influenced by some or like mixes in some of these style aspects, right? So basically that they are not mixed together or confounded somehow. Right. So basically a loss function or a general loss that leads to this disentanglement is like a general training loss where we first want to have a reconstruction minimization. So we have, let me check. Yeah, so it's the similarity between images, like latent vectors of the same content images. And in the end, what we have here is basically a differential entropy or general entropy, which basically means that if we only look at the contents part of our vector, we don't want to have variation within that. Like if we switch between or consider images of the same class, we would like to have our content part of this latent vector to be precisely like invariant, to be the same value for all of those images. Basically, we say, okay, it shouldn't care about the style, like some part of this vector should only consider the content. And this is because if you look at uniform distributions, the uniform distribution is basically the distribution that maximizes the entropy. So it's a sort of mathematical trick to formulate that we want to have equal likelihood for all of these images to produce the same vector. Yeah, and an important result here basically is under this or this very particular setting where we have these paired data and where we train with the contrastive loss, that then asymptotically these networks isolate content from style. So basically, this was shown before the sim CLR that it like works really well if you have that kind of data. That it like really well disentangles content from style. And this paper basically showed with a like causal setting why this is the case. And yeah, so basically for all these contrastive learning settings, you can probably do a similar proof. But what we have looked at for now was like a very particular thing where we had like predefined content and style groups or variables, even though we might not know it. We assumed that the data was somehow paired or structured. And what we would like to have is more general settings. So now we will have a look at some of those other techniques which are commonly used. So maybe one small note, this whole area is still under development. There's still ongoing research. Some of these approaches might be better suited for application in your like everyday models. Others might require very specific assumptions or constraints. But I want to give you a like brief overlook or overview. We will not go into like the very deep mathematical details, but I will show you like the overall intuition. So the common setting, if we are talking about CRL, is that we have some underlying latent process between the set variables. So again, we have some structural equations F that relate all of this to each other. Again, or mostly we assume the structural equations are like form a DAG, some cyclic graph. And usually these variables are not observed. And what then happens if this process is computed? We take a mixing function g, which then produces our output. So this might be like some underlying maybe genes, how they developed, and we see then the final plant or whatever in our lab. Or it might be that we have some underlying cells in memory, and G is the rendering function of our scene or of our game or whatever. So basically, then we observe these axes, and they might be a like arbitrary combination of these sets via this function G. So this is the setting, even in temporal settings and so on, that is commonly assumed. And in the simplest form, this G is some linear transformation, so just a matrix multiplication. And the problem or the unfortunate fact here is that in the general case, this is underdetermined and therefore the latent structure is unidentifiable. So basically what this means is that, yeah, there are a lot of cases where A might, like, we observe data, but we can construct a lot of A's or a lot of functions G of its parameterization, which correspond to some DAG of this process that we observe, but it might be not the right one. So, for example, oftentimes if we have maybe just a rotation in A, we might not know how much this stuff is rotated. So without further assumption, we can't like fix a unique function. And this is what we want to do, right? If we talk about recovering these sets, what we mean is that we want to have a unique distribution, that we want to be able to uniquely invert this process that created this image in the first place. So maybe I will have it on the other slides, but one very common thing is that if we have such linear transforms or different transforms, this is usually identifiable up to some like equivalence class. Basically, what this means, if I have this sort of transform, I don't make a lot of assumptions. It might be that I swap the variable order, right? So that I permute the indexing of the set variables. Basically, this doesn't harm me as long as I'm also like swapping all the edges in the same order. So usually identifiability is up to permutation, except if I make some assumption where I can really bind one of these z variables to one specific x variable, to one specific observation. Then, I mean, I know the order because I bind them together, but otherwise there might be flips or whatever, but we are okay with it as long as the graph structure itself is recovered. Yeah. So how do these additional assumptions look like? Basically, what we can do is we can say, well, maybe there isn't any causal transitions or causal links in my set values, and maybe I have non-Gaussian latents. So this is the noise that goes in this set. And what we get then in this setting, if we delete all the links from F, is basically an ICA setting, so independent component analysis, right? So I'm not sure if you have seen that before. So if you know PCA, basically PCA requires your components to be orthogonal to each other. And I think ICA only requires independence, so they might not need to be orthogonal. But so this is an often used result in like non-causal identification, which basically tells us, okay, under some conditions from sufficient observations X, I can recover my original variables, although it assumes that there are no causal interactions happening between those variables, that they were independent. Another thing to break this undefinedness or underspecifiedness is to have interventional data, and we will look at some algorithms there. Basically, what this means is, or what is often done is, I have an agent in some sort of environment, and this agent does some action. I know this action. Maybe I also know which variable is affected or which variable I want to like interact with. But the problem is the feedback I get is not in the sense that I now see in a particular set, okay, this set has now this or that value, because those are usually unobserved. But what I see through my camera is, okay, how did the image change that I now observe? And I know maybe I opened the door or like, yeah, turned a knob or something, but I need to now connect these actions that I did on the set, or these interventions, to my observations in the image. So this then helps us because I know which variables should have changed. I might be able to identify this process. So which changes in set propagate to which pixels in the image, for example. And the third thing is, of course, I can make additional structural assumptions that like restrict the class of functions, of mixing functions that I can have. And sometimes people assume that these variable set have pure children, which basically means, okay, there is at least one variable which is like a pure or only child of one of the sets. So the sets has one child which is not influenced by any other variable. So, I mean, under some conditions that might be true, I would argue, especially like if you're in an image domain, there's a pretty good chance that like camera angles or whatever, like they always influence all of your axes, so you seldomly have that setting. But in highly controlled setting, you might be lucky and get this kind of scenario. The other thing, of course, is time series, because if I know that I don't only have a like random collection of images, but I know two images are like a series of images, they are always consecutive to each other, then I can reason about the dynamics of my system. So maybe I approximate the physics that are like going on without interventions and whatever. And now if I have one observation and I transition to the next one, I can reason about what should happen in my underlying process. And from that, I can reason how should my image look like. So there again, it requires some more assumption than that. So just having a time series isn't enough, but at least it somehow binds together observations, which makes the structure or these assumptions I can make on the structure stronger. Yeah, as I said, so if we are looking at causal representation learning, so okay, there's still BSS, which is like in the non-causal sense, it's blind source separation, which basically means we have some latent factors. We observe a single signal and we want to separate out the original factors again. But basically the setting here is that we have again our underlying process. We have for every of those time steps, we have a mixing function. And this mixing function is only taking variables of the current time step, like the sets of the current time steps, so it doesn't mix between time steps to get an observation. And then again, this f function, this process function moves the latent vector from the last time step to the current one, or from the current one to the next one. And depending on the assumptions, there might be causal links between these sets at the current time step. So we have instantaneous effects. Many works also assume that we don't have these instantaneous effects, but that every causal effect is only between variables of the last time step to the next one. This sometimes makes identification of the causal structure a bit easier. But again, we see this underlying process F and this mixing function G, even in this time series setting. So, yeah, maybe let's start with looking at identifiability under interventions, because I think this is quite nice or intuitive. So basically, we are first in a very, like in this very simple setting, where again, we have some latent vector set. We have a linear process. So the latent causal model or structural equations F are linear. So it's some sort of matrix plus a noise. And also the mixing function is linear. So it's some sort of matrix that translates my latent variables to my observations. A general thing that we more or less always needs is that this mixing function, that its full column rank, which basically means in this setting, so we don't consider time or something. If I have less observed variables than I have latent variables, it requires me to mix together some of the latent variables, right? So basically, I need to be able to invert my mixing function, but I can't do that if it isn't full rank. So this is like basic first or second year math. So really, this is some assumption. This might be a strong assumption, but usually if you consider, for example, images or whatever, where I have like 10 or 100,000 of pixels, and then I usually in my VIEs have latent vectors of maybe 100 variables or 1,000 variables. So just to make sure if we are like in this very low dimensional settings where we really only look at maybe tabular data, I need to have enough observations such that I can at least reasonably assume that this mixing function is invertible. Independent of whether I can identify this mixing function in the first place. And here in this setting or in this paper, they assume that we have different contexts, and every of those contexts, oh, it should start at 0 actually. I have a perfect intervention on any of my latent variables. So every variable, every latent variable is intervened at least once. And I have this 0 context, which is the observational case where I don't have an intervention. Right. So this can be, so here all these contexts are always indexed with K, with a subscript. And usually, or as you might have seen before, for this latent process set, it's this equality where I have my transition matrix A times the vector set plus some sort of noise. So basically, here it's parameterized in a sense where then if I solve for this set, right? So I want to compute it from my noise, basically, I get this sort of parameterization, which might look a bit strange. So this omega is basically how the noise distributes across all the nodes. So it's this compact representation that you might have seen in the last lecture. Basically, we don't compute like the variables independently or like iteratively, but here we basically really have this matrix B that if we have it, we just multiply it once with the noise and get out the resulting set vectors. Right, then there is some notation. It will become clearer in the next slide. But basically we need to be able to invert these processes. And again, we might want to we want to identify all those sets. We want to identify this B, which is basically the reverse or this compacted representation. And because might be a bit ambiguous or is up to permutation, we just assume that this B will be upper triangular. Right. So again, this generating process here in this figure, we have some noise term. Via the inverse of this B matrix, we get to the variable set. Then by multiplying by G, we get to our observations. And again, the inverse of G is H. So yeah, they use a pseudo inverse or like a general inverse, however you compute it, to get back to set. And then again, applying B gives you the noise terms again. And the question now is really, can we recover all of those terms? So at each of those arrows, there are always the inverse, right? So it's sufficient to discover one of those. And we make some assumptions. So the covariance of the noise terms is the identity matrix. Basically, this means they are like not confounded, so they are all independent of each other. This common assumption that we always make. Then the authors define some covariance of Z in terms of B. And in the end, we also define this covariance of X under a particular setting, and we just assign beta K as a symbol for that. So basically, this is the covariance at every of those three levels that we have. Yep. And the only thing of those terms that we observe are our thetas for every of those interventions. And we wonder whether we can recover like the different factors, and especially these B's, which are like dependent on the current intervention. So because there we change the causal structure. G and H, these functions are independent of our interventions. They always stay the same because they always mix the latent variables that we then observe after the intervention just to get set, but they don't care about the intervention. So the result that people got is that the setting that we considered or described is sufficient and in the worst case also necessary. So we need always like as many interventions as we have latent variables. But if we have those kind of data, we can always discover like the latent process, the latent causal graph and variables. If we have less interventions, in some scenarios, it might work out, but there are then always causal graphs where it might fail or become ambiguous. So we always need all of those interventions to be sure. And so again, this I won't go into the details because it's like would take the whole lecture. But basically, what we do is we look at those individual thetas from all these observations. And what we see is that we take the differences of those. The resulting matrix will be of rank 2, like in terms of like, I think, column or row rank. But the exception is if we are at source nodes. So this is basically to say if you intervene on a variable which has no parents, we do not cut any we do not cut any edges. And for that, our process or like these covariances that we observe, they will not change, right? So this is the underlying intuition here, like interventions on nodes without parents, like they don't change the causal graph, and therefore our statistics that we observe in our observations, they will not change. And then what we need to do is, once we have observed all those source nodes, we remove them from our observation, and this is where it actually becomes tricky, because then we remove them and do the search again. But in this new search, we need to basically project the remaining system onto the orthogonal space without the removed nodes, which is a bit involved, and we won't do it here. But like, just keep in mind that we can just do this the step over and over again, always find those nodes without parents, because we can identify them from like the statistics, and then just remove them and iterate until we have found all variables, or like have discovered all variables. Right. So then maybe look at the temporal setting. So there is a bunch of works by Philip Repr and so on. Basically, it's there is a method called citrus, and here we have a setting of I citrus, and this I citrus it is for instantaneous citrus. So basically, in this causal graph, you allow for instantaneous causal links, but we will look at the like original only citrus version. What they all have in common is, again, that we look at temporal causal graphs with interventions. So this is really then your like reinforcement learning or like agent setting, where your agent takes an action and you observe the outcome in the next time step, in the next frame of your simulator or image. So yeah, we have this temporal structure that we discussed before, and we assume, actually, I think one of those interventions, like the right one, should be IT without the -1. But we will look at those and say, okay, we have an agent that takes actions, and here our agent actually knows which of those latent variables it targets. So this is important because it will be relaxed later on. So this is a strong assumption. We basically know which kind of variables should be there in the environment. And we also know, whenever we take an action, which of those latent variables we target. So this basically helps us with identification. Yeah, so this is basically the same graph as before, only for like one transition. Yeah, again, temporal causal relations, we have interventions, and we have latent confounding. So basically this agent might take several interventions, might like modify several causal variables or latent variables. And then again, in the end, we get some observation. They name the setting temporal intervened sequences. And the assumption is that between every time step, the latent causal graph stays the same. So it's a stationary graph. As we discussed before, we assume no instantaneous causal effects. And at every time step, the agent takes an action. Of course, I mean, the agent might also decide to take no action, but yeah, that's at least how it's modeled. So what can we do with that? So I think it's kind of intuitive if you don't look too deeply into into the maths. So basically the loss term again is, or the assumption again is that we work on image data, that we have some autoencoding setting. So basically you take the image, have some neural network that encodes it into a latent vector. And from this latent vector, again, you want to decode it back to an image. And the idea here really is to leverage that temporal structure, which tells us, okay, if I am at some time step t-1, I take my encoder to get a latent vector, and then I have some sort of function, some transition prior, which tells me, well, in combination with the agent action, how should my latent vector change to the next time step? And what I want to have is that my prediction of this latent vector on the next time step should be the same as what my encoder tells me. So, right? So both of these, like taking the last time step and progressing the image in the latent space, should be the same as like just observing the next time step and then encoding it into the latent vector. So those two need to be the same. And then within a single time step, so this was the step 2, actually, the transition dynamics between time steps. And of course, we can always do the standard autoencoder loss, where we look at a single time step, encode the image, decode the image, and the original image and the decoded image should be the same. Yeah, and this transition prior, basically, they do some sort of like bit more complicated stuff here. Basically, what they assume that my latent variables might be multi-valued, so that I take an intervention which might affect actually multiple variables. So they first need to like decode that and basically encode that a bit. But the overall idea is that to leverage this structure. Yeah, and under some more assumptions, I think some smoothness assumptions and so on, they basically prove then that this setting recovers your original causal structure, or at least it recovers your causal variables, the latent causal process. You might not directly get the causal structure because it's or the causal graph because it's encoded in the encoder and decoder. Of course, you can then look at like explainability methods, GradCam or whatever to figure out the areas in the image that affect individual latent variables. And if you have those latent variables, you might as well also just run a causal discovery method on it, right? So generalization of that is BISCIT, so causal representation learning from binary interactions. And this basically drops the constraint that we need to know which variables we are intervening on. So basically what this says is I only observe now a vector of binary interactions, which means I know my agent like lifts an object, my agent opens a door, but I do not know which of my latent variables corresponds or like will react to those interactions. Basically, I tell my agent, oh, do this or that, and I want to figure out still the causal graph without knowing which of those latent variables are targeted. And just to give a high level idea, so we no longer know which interactions or interventions target which variables. So basically we need to find a mapping from the interventions to the variables. And what we can do is find basically transformations. Here it's depicted with rotations that disentangle or like transform the latent variables or the interventions in a way that they are no longer mixed, so that every intervention I make corresponds to a single variable in my latent vector. So this is also some assumption that they make, that here again, interventions do not affect multiple variables. So every intervention is assumed to exactly influence a single variable, which might also be tricky. But the overall idea I find really interesting. So basically what this means is if I have two interventions, I1 and I2, and I just have data where those two were applied, and I look at some sort of latent vector, which I, let's say, somehow recovered. How do I know whether my latent vector is actually correctly decoded? So whether it's not somehow rotated so that variables are maybe mixed together in some sort of sense. Basically, the idea is if I do this, then only one of those latent vectors should be affected. If I have a rotated perspective or representation, then I will see multiple variables being affected. And another thing is that might also be or like good to check is when I see scenarios where I take two interactions at the same time, two interventions at the same time, they should correspond in my latent vectors to the same as if I took those two like individually or yeah, like maybe let's assume no dynamics in the system if I took those two one after another. So basically, I don't know, opening a cupboard and taking something out of it, whether I do it in a single time step or in two time steps, shouldn't like really matter in a simplified scenario. Right. So basically, again, from all those temporal dynamics, we might recover or figure out the mixing function or otherwise the unmixing function. And then I might have identified my latent space up to rotation. And then if I look at those binary interaction vectors, I really only need to find a rotation that basically disentangles those such that every interaction only alters a single variable in my latent vector. So really, as I said, it's a very high-level approach or high-level intuition. But yeah, I just found this trick or idea maybe quite useful. So yeah, then this might relate already to the next section. But what they additionally assume is that any two variables are not always intervened jointly, which basically means, okay, I sometimes observe at least that a variable is intervened independently. On the opposite, sometimes I want to have any two variables intervene jointly, basically to do this check whether like doing two interventions like after each other or at the same time, whether that like gives me some sort of equality. And the third thing is that mechanisms basically vary over time through interactions. So that means that every of those mechanisms is somehow affected by my interactions, so that I don't have a mechanism which is never changed, maybe some what we discussed in the beginning, some constant mechanism or something where I never see an interaction, because if I never seen interaction, I cannot assign any cause or effect to it. And yeah, a nice result that I got is that I need log k actions. Okay, so the next thing is that we want to look at identifiability under sufficient variation. Basically, again, we are in a time series setting, and here the authors, at least in this paper, assume like a sparse latent process, which basically means this latent process, it can't be a function which is like fully connected, like every variable influences every other, but there need to be some edges missing. Again, like I won't go into the details here, but it's just required for this case. The more important thing is that here we don't make so many like assumption about the structure, and we don't have interventions. Basically, the thing that we now need to do is, or what we can do is that the general case again is unidentifiable, but we might place particular like assumptions or restrictions on our data to make it identifiable. Basically, what you also see from like equation solving and basic maths, that we construct a system of equations which need to have a unique solution, and the things that the authors like leverage is that they first enforce the independencies or encode the independencies of the graph. So basically, this sparseness of the latent transitions, and also that like the mixing function, that it can't mix in latent factors from a previous time step, so that it always like only is from the current time step. So we won't like consider what these variables like mean in detail. Basically, what this is the sufficient variability constraint from the paper. And what you can see is that it really leverages some sort of like gradients. So we have 3 different groups, and those groups basically restrict like the change of the mean and the change of the variance, or they at least how do I say this? They require those gradients of the mean and the variances and so on to have sufficient variability. So if you construct this sort of vector, the theorem that the authors propose is that you need to have a particular number of rows from your observations, and those rows that you then like get, they need to be like at least 4n plus some constant of those need to be linearly independent. Basically, this means, okay, I need to have sufficiently independent rows or observations to solve this the system of equations that I have. And really, we won't look into it much further. Yeah, so in encoding this graph structure, what it really means is, or says, is that we have some sort of sparsity. Basically, the C's is a like, maybe go back to the last slide. So those C's are basically all variables from the current time step and the last time step. So the authors like generalize to like also a series of past time steps, but we only look at the single leg case. And yeah, what it tells us is that those variables can only be connected in a particular way. They basically tell us the variables that I observe or have, they need to be sparsely connected. So this tells me, okay, I have at most one parent in CK or L. And the other thing tells me that I can't have disconnected variables in those Cs. So I always need one parent at least. Oh no, it's the other way around, sorry. So the one tells me I need at least a parent, the other one tells me I can't have like more than two. And there is some like quite old result, which basically tells us that these independent structures are somehow related to these cross derivatives. And this is basically what we saw in the previous slide. So basically, this constructs then a like system of equations, which basically tell us or mathematically encode these independence conditions. And here the first two ones correspond to the statements above. Like you can look into the paper, it takes a while to also get through all the notations and so on. But basically, what it does is really encode this graph structure and then require like place some additional variability constraints on those gradients that basically tell you, okay, under which conditions am I able to solve this set of equations uniquely? Yeah. And then I think that's it. I'm sorry that it was a bit too high level. The thing is, I placed all the papers as citations, but I wanted to give you the like general idea. Feel free to ask if you have any particular questions or look into the paper if you want to know more. The problem usually is that these kind of algorithms then get very involved and mathematical, and like you could make a lecture of like out of any of those algorithms individually. But in summary, the insight I wanted to show you is that somehow it's just equation solving, right? Because if we look or remember these causal structures, we didn't care so much about we care about the causal direction, but really it's about like having those mixing functions and inverting those. Because once we can invert those mixing functions and recover the underlying causal factors, we can always just apply causal discovery or something. And so then we are done. And for these mixing functions to be invertible, it's basically solving some matrix equation, or in the nonlinear case, solving like for some constraints and making sure that we can find a unique solution to invert those mixings. And the main two categories, as we've seen, is either to have interventions in settings where we have, for example, agents or like carry out experiments, maybe in a lab or in the real world. And the second type of conditions that we can leverage is to have sufficient variability, which basically means our data is diverse enough and the interactions of my mixing functions are like complex enough or like maybe non-linear and so on, that I'm always able to find a unique solution and recover my underlying variables. And then in this time series setting, again, we also leverage those temporal constraints by approximating the temporal dynamics and then equating the dynamics that we approximate in the latent space to the dynamics that we actually observe in the images. So in this lecture, we considered usually models that we trained from the ground up, models that we trained on particular data sets, usually like small experimental data or like reinforcement learning data. But as we discussed, usually we require interactions, we require sufficient variability, and this is oftentimes limited by the data that we have available, by the compute that we get. But the other idea that we discussed at the very beginning was, okay, maybe I can have prior knowledge. Maybe I have large scale models that are already trained. And maybe training a large language models, like putting all of the internet into my model. Maybe this gives enough variation and makes the data diverse enough to have LLMs develop an understanding of causality. So this idea is questionable, I think. So, of course, by now, these companies train LLMs with specific data sets that allow them to understand or like at least develop circuits for reasoning and also for causal inference, or at least for causal reasoning. But yeah, so we will consider this aspect then in the next lecture and have a look at like more modern models, at those foundational models, whether they really evolve causal understanding. That's it for today. Thank you and see you next week.